I'm approaching this whole class with the idea that we need a general idea of what happens by hand, but we're going to rely pretty heavily on Desmos to help us out with this as well, because we are going to need to know what to do there. So, we're going to start with making just a basic table. What is a little bit different about exponentials and logs is they can have so many different bases. So when we talk about an absolute value graph, we are starting with the same graph every time. We start with that V-shaped graph, right? And then we move it up, down, left, right. We flip it upside down. We can do all of that stuff. But exponentials and logs are a little bit different because the base can be a different number. So we might have 2 to the x power, but we might also have 8 to the x power, or e to the x power, right? So that makes these a little bit different, but let's get just a general picture. And I used 2 to the x power here for this first one just because it was a pretty easy number to deal with, and it doesn't get too big too fast, although it gets big kind of fast, right? So let's plug in some numbers into this equation and make ourselves a table, right? Because if we plug in numbers, it gives us the y-coordinate, and then we can just graph those points, and that gives us a picture of what the graph looks like. So, I'm gonna hold off. Anybody know what to do with y equals 2 to the negative 1? Type in your calculator. Tell me what it is. We'll go ahead and do it with the calculator. 2 to the negative 1. It is 0.5. Anybody know why in the world that's 0.5? And why it's not negative? Okay, but why didn't it turn it negative? Anybody know what to do with it? Have you guys seen negative exponents before? We do them a little tiny bit in Math 1, but I don't really expect that you remember it well. Negative exponents, when I teach it like I tell you that if you had me, I told you that negative exponents were like bad children. And what should you do to bad children? Lock them in the basement. It'll fix all their behavior. It'll turn their exponents positive. See, you guys did remember that, didn't you? So what happens when you have 2 to the negative 1, you got to send that bad child to the basement. It's going to fix their behavior if you just lock them in the basement for a little while. It'll make their exponent turn positive. Now they're a good child again. You do have to put a 1 there on top because you can't just leave nothing on the top there. So this is just 1/2. That's why we're getting 0.5, right? So there'll be some places where we got to look at negative exponents later, but right now that's good enough. So what about 2 to the 0 power? What do I get when I do 2 to the 0? Is 1. Anything to the 0 power is 1. What is 2 to the first power? 2. 2 to the second? 4. 2 to the third? 8. Okay, I just did a little tiny piece of this table here because a lot of it won't fit if we go past there, right? 2 to the 4th is going to be 16. It runs out off the graph. So if I graph these points, I've got negative 1, 1/2. That's right here. 0, 1. I've got 1, 2. I've got 2, 4. I've got 4, 8. Right here. Now, you can kind of see what's happening here. What we've got there is exponential growth. If it depends on who you had for Math 1, but if you had me, I know that we do several things. We do like the pay it forward thing where you do 3 good deeds for somebody, and then they do 3 good deeds for somebody, and I have you guys guess, and you guess it's going to be like, 10 or like 100 or something, and then it's actually like after 10 rounds, it's actually like 56,000 or something like that. It grows really, really fast, right? Exponential growth grows really fast. What happens on this end, though? What happens over here? Okay, you say it's flat, right? Will this ever become negative? Will it ever drop down here? Because negative exponents, even if I did like 2 to the negative 5th, right? That would be 1 over 2 to the 5th power, which would be 1 over, let's see, 2 to the 5th would be 32, right? So if I try to graph that, -5, 1 over 32 is like 0.03 or something like that. It's really small. It's going to almost be to that line, but it's not going to actually touch. So it's going to look like this. If you graph it on Desmos or if you graph it by hand, it looks like it touches that line, but it doesn't. Here's why, okay? So let's think this is applicable for this. So let's say that I'm going to walk to the cabinet over there, all right? I'm going to walk to the cabinet by going halfway to the cabinet each time, okay? So if I walk halfway to the cabinet, that puts me about right here. Okay, I went about halfway. If I go halfway again, that will put me about right here. Okay? If I go halfway to the cabinet again, I got 4 blocks right here, so I'm going to go halfway. There's 2 of them. So I'm here. If I go halfway to the cabinet again, I would go, there's 2 blocks left, I'd go 1 block. Right? If I go halfway, I'm not skinny enough to pull this off at this point. If I go halfway, I'm going like half a block. Now, obviously I'm touching my cabinet here. Theoretically, mathematically, do I ever get to the cabinet? I never get there, right? I just keep going these teeny, tiny, increments towards the cabinet, but I never actually get there. That's what's happening right here on this side of the graph, okay? We're getting closer and closer and closer and closer to that line, but you never actually get there. Now, when you graph it on Desmos, it's going to look like you touch that line. But if you zoom in enough, it'll start spacing out and you're not touching the line anymore. And then you can go over and it looks like it's touching the line. But if you zoom in enough, eventually you'll get to where Desmos can't zoom in anymore. But it's going to look like it touches, but it doesn't. So for exponentials, this is important right here. In fact, I'll tell you what, let me go ahead and do this. I am going to let you guys use a note card on this test as well. Let me do the picture this time. And this is something I would add to the note card right here. So this will help you a lot. Alright, so you can have a note card for the test. We're testing Thursday next week, so you still got a little while, but I'm going to go ahead and give this to you because you may want to add to it while we're going over notes. And you may use this. You may write front and back as tiny as you want. You are not allowed any magnifying devices. So you can't bring in a magnifying glass to read your note card. But as long as you can read it with your bare eyeballs. I mean, you can wear your normal glasses, but you can't. If you go to dollar store and buy you some reading glasses so you can really zoom in, I guess I can allow that. No magnifying glasses. Alright, so note card, you may put anything you would like on that note card. You may use it on your test. So the domain of an exponential is always negative infinity to positive infinity. Okay? The only exception would be if I gave like crazy exponentials where it was like 2 to the square root of x minus 5 or something like that. I'm not going to give you something like that. Any exponential you're going to see in this class is going to have a domain of negative infinity to positive infinity. Or you may see it as all real numbers. So if it's written out, it would be called all real numbers. Okay? This is always the case. You might want to write that down. Domain, exponential, always going to be negative infinity to infinity. This is helpful because on your test or quiz, you are going to have problems. And they're going to give you y equals 2 to the x minus 4. And it's going to say, what's the domain? What is the answer? All real numbers, or negative infinity to positive infinity. You don't even have to graph it. You don't even have to think about it. Exponentials are going to have a domain of all real numbers. Okay? So that'll be very helpful for you to have on your note card. The range, on the other hand, is, I'm not going to put exactly what it is, it's always restricted. So that means not all real numbers. So for the ones that we will look at, you're not going to see any exponential functions that have a range of all real numbers. It's always going to be something like 2 to infinity or negative infinity to 3. Okay, so you will not see any where the answer is all, where your range is all real numbers. Okay, questions? Okay, everybody had a chance to get those down? All right. Okay, horizontal asymptote. So what I just demonstrated right there is I was trying to walk to the cabinet by going halfway. All right, is what we call asymptotic or asymptotic behavior. It was creating an asymptote. I was getting closer. In this particular case, you can think of, you know, that closet. Well, it's kind of two-dimensional. It's not. It's one-dimensional, sort of, so it's a little bit different. But you're getting closer and closer and closer to a line. So an asymptote, you can have horizontal or vertical asymptotes. Everybody put your arms out and show me a horizontal line. Horizontal is this way, right? Everybody show me vertical. This way, all right? So we got those two terms there. We can have horizontal and vertical. An exponential function will have horizontal asymptotes. So what this means is there's going to be a horizontal line, and you are going to get closer and closer and closer to that line as you approach. As you approach that line, you get closer and closer and closer, but you don't touch. Just like theoretically, I would never touch that cabinet, right? If I just went halfway. So all exponential functions that we will look at in this course have horizontal asymptotes. Okay. The equation of a horizontal line, if I want to write the equation of this line right there, what is it? Somebody know? This is the easiest thing in the world. We do it in math. You do it in 8th grade. You do it in math 1. You do it again in math 2. Here we are in 3 doing this. What? It's not. It's y. It's y equals a number. So, like, for example, this one is y equals -3. Okay, so it's going to be y equals just a single number, right? It's backwards because the y-axis is the vertical axis, right? But y equals is a horizontal line. The reason that is, if you think about the points on this line, right there, the coordinates of that point is 1, -3. The coordinates of this point right here, 6, -3. The coordinates of this point right here, -5, -3. What's the same on all of those coordinates? The y, and that y is -3, right? So that's why this is y equals -3. All the points on that line have a y coordinate of 3. This is something that, you know, my calculus kids are still messing up. Because it just somehow is like the easiest thing in the world, and it's so easy to forget as well. But y equals is a horizontal line. Okay? And you'll need to know the difference because some of these are going to be like multiple choice questions, and they're going to ask for a horizontal asymptote, and they're going to put like x equals 3 as the answer. And you can throw that out because it is a vertical line. All right? So let's continue here. All right, end behavior. We were really probably supposed to talk about this with absolute values, and I forgot to put it on the notes. So when we were doing all that domain and range stuff, we were supposed to talk about end behavior, and I forgot to include it, but I about decided there was already about too much in that anyway, and it might not hurt to save it to here anyway. So what we're sometimes interested in finding is what happens for really big numbers at the ends of the graph, right? when you go towards infinity or towards negative infinity. We might be interested in seeing what happens for really, really, really big numbers. So, to describe this, we would say as x approaches negative infinity. So when we see the beginning of this is for exponentials will always start this way. This means we're looking at the left side of the graph, because on the axis over here, negative infinity is over here on this side. Positive infinity is on this side. So it's the only time you're going to kind of like start from the middle and see what's happening out towards the end, right? So as x approaches infinity, we will say y or sometimes f of x. It just depends. Remember, we can kind of use those interchangeably. Your y or your f of x approaches some value, okay? It could be positive infinity. It could be negative infinity. It might be a number. Okay, we're going to do some examples here. And then you also want to describe what happens on the other side of the graph. So this stuff right here, as x approaches positive infinity, that means we're looking at the right side. Let me change the colors there. Of the graph. We're looking at what happens out here towards positive infinity. And so as you go further on the right side, you're either going to see the graph go up forever, down forever, or even out at a number. Okay, so we're going to talk about that. We'll do some examples of those. Okay? All right. Okay, here's an example. Domain, range, asymptotes, and end behavior is what we're really going to focus on for these problems. Okay? All right, so here is a graph of y equals 1/2 times 3 to the x power minus 4. Tomorrow we're going to talk some about transformations, moving things up, down, left, or right, but remember we can use Desmos on everything. So I'm either going to give you a picture of the graph, or you're going to be able to type it into Desmos to look at a picture of the graph. I just put the picture here so we didn't have to type it in. So the first question should be an easy question. Oops, I did not mean to do that. First question should be an easy question, because you just wrote something hopefully on your note card, or at least on your notes. What is the domain for this example? Negative infinity to positive infinity. Okay, that's always the domain for exponentials. Sometimes it looks like it stops, because what happens with exponential growth is it gets really steep at the end. So sometimes, I keep losing my glasses. Sometimes whenever you're looking at this, yeah, it's pretty clear that we touched the graph way over here. Sometimes it looks like, oh, well, maybe out here it doesn't touch because maybe there's a vertical asymptote there. Exponentials don't have vertical asymptotes, okay? It's always negative infinity to positive infinity. Sometimes the graph doesn't look like it because it's really steep, but it doesn't. However, the range, I told you, is always restricted. If I look at this graph, if I'm thinking about doing the range here, I'm looking at the vertical axis here. What is the lowest point on this graph? For y-axis, what's the very lowest it goes? -4. In fact, I could go right here, and I could draw in this little dotted line right here. Right there at -4. Because I know exponentials have this happen, what does that green line ever actually touch my dotted pink line? It does not. Now it's going to look like it does on the paper, right? Because we can't zoom in enough to see that. But it never actually gets there. So when I put a 4 right here, should I use a parentheses or should I use a bracket? Parentheses, because it never touches that line. In fact, you're going to see, use parentheses for everything, for domain and range for this, because these have asymptotes, so they don't actually touch those values. So my range would be 4 up to, how high, what's my highest point? Where does it go? It goes up forever. It goes to positive infinity. Right there. Now, whatever number you have right here, should have something to do with your asymptote, right? Because right here, we have this line, and that is, we get closer and closer and closer to that line, but we never touch that line, okay? This is a horizontal asymptote. How do I write the equation of that pink line that I drew in right there? Y, oh, I should have a negative 4. Y equals negative 4. Okay? It is a y equals line because horizontal lines are y equals. You can also see, like, think about where it crosses. It crosses right here. That's on where y equals negative 4. Not x equals negative 4, but y equals negative 4 right there. Okay? Everybody all right there? All right. End behavior we haven't looked at yet, so let's talk about this a little bit. As x approaches negative infinity, okay? Negative infinity is over here on the left side. So when we see this part, it'll always look like that at the beginning. As x approaches negative infinity, that means the left side. Okay? So if I think about starting here somewhere in the middle and going to the left side, what's happening to my y values? Am I going up forever, down forever, or am I evening out at a number? Evening out a number. What is that number? What number do I get closer and closer and closer to? Negative 4. So y approaches negative 4. That's on the left side of the graph. Okay? This stuff right here is as x approaches positive infinity. The x-axis positive infinity, that's over here. That's the right side of the graph. So that means I'm starting right here, and I'm going this way. Okay? What happens on that side? Do I go up forever, down forever, or do I even out at a number? Up forever. So that's going to be what? Infinity. Positive infinity. So if on that side the graph goes up, you're going to put positive infinity. If it goes down, you're going to put negative infinity. If it evens out at a number, you put that number. This number right here that you got for range is going to be the same number you use over here. Now, it depends on what the graph looks like. There are some where the negative 4 would go like right here for the second one. So you just have to look at your picture and see what's happening. That x approaches negative infinity is always the left side. And the left side's where we saw this kind of like even out at the number, right? On the right side, it went up forever. So that's where we put the positive infinity. But yes, you should see that asymptote number being used over and over again. So it wouldn't be like you suddenly got a 3 in this problem or something. That should help too when you're looking at answer choices. All right, questions? All right, those are exponentials. Let's look at some logs. All right. All right, you can use your calculator or Desmos. I want you to type in all of those logs and give me, oh, let's see. Do you guys know how I go from decimals to fractions and Desmos or the calculator? I'll show you both. Let's see if it works. I don't know if it works with the logs. Hopefully it does. Let's see. Oh, wait. Here we go. Okay. When you type in log base 2 of 0, log base 2 of 1, log base, let me go ahead and do log base 2 of 3. Okay. We'll do it with logs. It's okay if we don't have fractions. It'll be fine. I don't want to go through how to get fractions. Just type those in. Get your values right there. If you do need to turn something into a fraction, let's say you were doing 12 plus 7 divided by 9 minus 1.5 or something like that. If you're on Desmos and you do want to change it to fractions, see right here where I've got that little button right there. If you click on it, it'll change your answer to a fraction if you need a fraction for some reason. Sometimes, like with the log, it couldn't do it. It wasn't a number it could change to a fraction. Okay. What happened when you guys put in -1? Undefined. put x. We got nothing. What about 0? Undefined. Okay. For 1, what'd you guys get? 0. What about for 2? 1. What about for 3? 5, 8, 5. There. So, I got 1, 0. I've got 2, 1. 3, I've got 0.15. Well, this does not show me a whole lot. Somebody type in 7 for me. Log base 2 of 7. See what you get for that. .807. So over here at 7, we got 2.807 about right here. Somebody do 10 for me. Alright, so 10 is 3.322 about here. So I can kind of tell over here it's looking something like this. Hello? Okay, alright, thank you. Passion, they need you in the office and bring whatever form you need signed. Alright, so I can kind of see what's happening here. Over here, somebody do 1/2. Do log base 2 of 1/2 for me. It's -1. So 1/2, -1. Somebody do like log base 2 of 1/10. Okay. 3.32. That's gonna be like here. Okay. When we put in 0 though, we got undefined, right? And -1 we got undefined. Okay. So what happens for logs is you have a vertical asymptote right there. It's going to look like it actually touches that vertical line, but it doesn't actually go there. Which kind of makes sense, because if you think back to what our graph of our exponential looked like, it looked, I'm going to draw this real quick, our exponential looks like this. So if we flip that over, the line y equals x, because they're inverses of each other, we should get something that is reflected right there. For these, and this might be something good to add to your note card, the domain of a logarithmic function is restricted, not all real numbers. Okay, but the range of a logarithmic function is always -infinity to infinity, or all real numbers. Notice how it switched? What do we do whenever we find the inverse of something? We switch to x and y. Does it make sense then that the domain and the range switched here? Domain is x's, range is y's. So we see that switched on log functions. So domain of exponentials is always all real numbers. Range of logarithmic functions is always all real numbers, right? This is, again, helpful when you get to the test, because if I ask you what is the range of log base 7 of x plus 3 minus 4, what is the range of that going to be? Without graphing it, I see it's a log function. Range is going to be -infinity to positive infinity, even without looking at it. Okay. All right. Questions? All right. Okay. So logarithmic functions. Oh, I did not fix this on my notes. Let's fix this. This is a mistake. All logarithmic, I copied and pasted that slide and I didn't fix it. Alright, so all logarithmic functions that we will look at in this course have vertical asymptotes. What's the equation of a horizontal line? Gosh, I didn't change that either. Change that to vertical. I copied and pasted that and then didn't fix it. Let me fix that. The equation of a vertical line, what is it going to be? X equals a number. So, like, if I'm looking at this line right here, what is the equation of that vertical line that I have graphed right there? X equals -2. And it helps to, like, look at where that line crosses an axis. It crosses right here. That's your x-axis. It equals -2. Right? Horizontal lines don't cross the x-axis unless it is the x-axis. They cross the y-axis. Okay? Alright, any questions so far? Alright. Let's move on. Okay, here's an example for a log. I've given you the graph. We need domain, range, and asymptote in behavior. Okay, in behavior is just a little bit different for these, and I'll show you why in a second. The graph of natural log of x minus 1 plus 3 is shown here. We'll start with range. What's my range? -infinity to +infinity, because it's always -infinity to +infinity for the log functions. Now, if I look over here at my graph, I said these always have vertical asymptotes. Where does this appear to have a vertical asymptote? At 1. So right here, we're going to get closer and closer and closer to that line, but we're not actually going to touch it. So, who can tell me the domain for this? It is 1 up to what? Infinity. Right? Remember, with that domain, we're going to cross. We don't even touch the graph over here. We never will, because it doesn't go over here at all. But as we go across, the graph starts at 1, and it continues on forever. So 1 to infinity. Okay, everybody okay? What's the equation of my asymptote here? X equals 1. So we're wanting the equation of that line right there, which is going to be just x equals a number, and it's going to be the number where it crosses the axis right there, x-axis at 1. That's what happens for that. So when it asks for an equation of asymptote, it's going to be x equals some sort of number. Now, I did my in behavior a little bit different for this, and I am not 100% sure you may see this either way, but I think it's going to appear the way that I have seen. Sometimes maybe they might put as x approaches -infinity for the left side, right? Because this one right here is left side. This is left. This part right here is the right. But if we start over here, do we approach -infinity? We never get past what number? 1. So I think what you're more likely to see is as x approaches 1 in this case, because you don't actually go to -infinity. Maybe some questions might still say -infinity, because -infinity is over here, and I guess as you go this way, you are getting closer to -infinity. It's just you never really get anywhere close to it because you stop at 1, right? So this is my left side. What happens as I go to the left side of the graph? It goes down, and down means that I need to put -infinity. Okay? Then if I do as x approaches positive infinity, that's the right side of the graph. So if I go to the right, what happens? Do I go up, down, or level out at a number? It kind of looks like it's leveling out. Is it leveling out? It's not. It's going to infinity. Logs don't level out. They don't have horizontal asymptotes. You're not going to have vertical and a horizontal asymptote at the same time. So for logs, these right here should be infinities. Positive or negative. They can switch which one's which, but they should not be leveling out at a number here. Sometimes they look like it when you graph it because they're not very steep. They look kind of flat, but they do continue to increase forever. Okay? All right, so we're going to talk about one more thing. All right, for exponential functions, way back in Math 1, long ago, your freshman year, when we were all still sitting here with masks on, y equals a times b to the x is your exponential form. A is your initial value. B is your growth or decay factor. Okay? X is some sort of time. All right, so we looked at that. The only thing I really want us to think about today is whether things are growing or decaying when we're talking about exponential. So, if I have exponential growth or decay, the way that I can tell is by looking at whatever number is being raised to the power. So this number right here that's being raised to the power tells me whether I have growth or decay. If that number is bigger than 1, then I have exponential growth. So some examples of exponential growth. If I have something like y equals 3 to the x, that's going to be exponential growth because the number I'm raising to the power is bigger than 1. If I have y equals 50 times 1.008 to the x power, what number am I raising to the power? The 1.008, is that growth or decay? Growth, because that number is bigger than 1, right? So you're looking for the number raised to the power. If it's bigger than 1, you have growth. Then, also for decay, I'm going to have a number between 0 and 1. I didn't say just less than 1, because if you start throwing negative numbers in there, crazy things start happening. We won't see those. So, a number between 0 and 1. Somebody give me a number between 0 and 1.
Oh,
No.
I'm sorry.
0.5. So if I have 0.5 to the x, that number right there being raised to the power, it's less than 1, so that's exponential decay. I might have one that looks like this. Y equals 5,000 times 0.89 to the x power. Would that one be growth or decay? That one's going to be decay because that number raised to the power is less than 1. But not negative, because if you have negative, crazy things go on. I'm not going to throw the negatives at you. But. All right, so let's look at this next thing here. So this should be real quick. All right, the first one, A, 100 times 0.12 to the x. Alex, is that growth or decay? Decay. Ooh, it's not used yellow. It's hard to see. Decay. Okay. Katie, what about B? Is that growth or decay? What? Growth. Good. Now I got a 0.2. Why is that not decay? That's not raised to the power, right? It's the 5 that's raised to the power. That's the number we care about. Okay? Let's see. Carlos, what about C? Growth or decay? It's decay. Because the number that you're raising to the power right here, it is less than 1. 1/2 is less than 1. Okay, we're going to talk more about this when we get to applications, but right now I just need you to be able to identify. Everybody all right there? Okay. All right. Okay, I want you to take a little bit of time here. Actually, let's do this. Let's do this. You guys and two in the back. I want you guys to do example 3 for me. You 4 right here, I want you guys to do example 4. Well, this is going to put all 6 of you, I want you guys to do example 5. And you 4, I want you guys to do example 6. Everybody know which example they've got? All right, so graph this in Desmos. It'll help you. Some of it, like,
Together or
you can work with each other if you want, but don't, like, move desk or anything. We're just going to do this real quick. So everybody try those. I'm going to hide my screen. Put this up here. EB is end behavior. And for end behavior, alright, so I'm here working on this. Alright, whenever it asks for end behavior, you're doing as x approaches negative infinity. If you want to use the arrow instead of writing approaches, you can. And then as x approaches positive infinity, that's what it's looking for there. Some of these will not have a y-intercept or an x-intercept, so just put none for those. Yes, it sometimes includes that same number, but the asymptote either needs to be x equals a number if it's a vertical asymptote, or y equals a number if it's a horizontal asymptote. Okay. All right, let's see what you guys have came up with. This over here. What did I just do? Where'd the... Okay. All right. First one, log y equals log base 2 of x plus 3. Okay, this was the first one over here. I'm going to zoom in, but I can't. All right, so let's see. Jason, what'd you get for domain? Negative. Oh, I don't think it's going to be negative 2. Here is some. Okay, what'd you get for your asymptote? Okay, so is it x equals or y equals? X equals negative 2. Don't write that down. So here's the trick. If you've got your asymptote, type it in over here. It'll also help you know if you did vertical or horizontal right. Is that the asymptote? No. That is where our x-intercept is at. But that is not our asymptote. Okay? Where should it be? Negative 3. Okay? Test it. Type it in to see right there. And you can see it looks like it touches, but if you zoom in, it's not really touching right there. So we should have x equals negative 3 for that one. I know some of you guys didn't have this one, but you can write it down as we do it. So our domain needs to be -3 to infinity, not -2. Range, what is that, Katie? For negative infinity to positive infinity, right? That's always the case for our logs. Okay. The x-intercept, what did you get for that one, William? Let's click. 0, 1.585. Okay. Does it? Oh, no. That's why. Does not count for everyday mistakes. I make too many of those. 0.1 point. Okay. All right. So, okay. All right. As x approaches, now technically on this side, do we approach negative infinity? Where do we stop on this graph? We don't go past -3. So as x approaches -3, what happens with our y? It goes down, and down is negative infinity. Okay? On the right side, as x approaches infinity, what does our y do? Positive infinity. It goes up. Okay, questions on that one? Alright, let's do x plus 1 plus 3. Okay? Alright, range for this one. It's a log. I already know it's going to be negative infinity to infinity. We're going to put that in. X-intercepts and y-intercepts are just reading those off of the graph. Y-intercept is at 0, 3. What'd you guys get for the x-intercept? Oh, sorry. Okay, now, okay, so there is no y-intercept then. Okay, what is the x-intercept? 125. Okay. Drew, what's the domain? Nope. 1 to infinity. Yeah. Because on this one, and see, I can go over here and change this to x equals 1, and I can see, oh yeah, that looks like the asymptote there. You'll also notice, like, whatever is inside of that, x minus 1, it can't equal 0 because you can't take a log of 0 or anything less than 0. So if you solve that, if you add the 1, I get x equals 1, that's my asymptote. So if you're given the equation, same thing was true here, x plus 3, you can find out what would make that 0. Subtract 3, x equals -3. That is going to be where your asymptote is at. Our asymptote for this one is x equals 1. As x approaches, do we approach negative infinity on this one? Nope, we hit this wall right here. Where do we approach? 1. What happens? X approaches negative infinity because as you go on the side, this side of the graph goes down. As x approaches positive infinity, what happens to the y? Y approaches positive infinity. There you go. Okay, we got 2 more. 2 to the x plus 3. Ooh, parentheses. Keep that x plus 3. All right. Oh, look. Does that have a vertical asymptote? It sure does look like it has a vertical asymptote whenever I graphed it. Does it? It does not because this is exponential. Look, it crosses that line. If you zoom out enough, it crosses the line. So this is not vertical. We'll get rid of that. Okay. What is domain for an exponential? Negative infinity, positive infinity, always. Okay. What's the range on this one? 0 to infinity. Okay? Does it have an x-intercept? None. Y-intercept? 0, 8. Okay? What's the equation for my asymptote? Y equals 0. Always type it in to make sure it looks right. Y equals 0. Yeah, that looks good. Okay? And end behavior as x approaches negative infinity, what happens to my y? So on the left side, we approach 0 because we even out at a number. Don't pack up yet. We got to do this last one. And as x approaches infinity, what does y approach? Positive infinity, because on this side, we go up. Okay, last one. Y equals 2 to the x minus 1 plus 3. All right. Okay. For this one over here, what did you guys get for domain? Very good. What about the range? Very good. 3 to infinity. X-intercept? None. Y-intercept? 0. 3.5. Okay, what's the asymptote for that graph? Okay, you can't just say 3. You gotta give me an equation. Y equals 3. And then, to make sure you got it right, go over here and type it in. Y equals 3. Oh yeah, that looks good. And then end behavior as x approaches negative infinity. What happens to that y? It approaches 3. As x approaches positive infinity, y approaches infinity. Okay. All right. So, let's see. We had, what else did we have to do here? Was that it? Okay, we got the notes done.